Imagine if we could bottle sunlight the way plants do, storing its energy not just as electricity, but as liquid fuels. Fuels that can be poured into ships, planes, and factories without adding new carbon to the atmosphere. That's the promise of artificial photosynthesis, often called the holy grail of clean energy. And now researchers at the University of Basel have taken a major step forward. They've built a single molecule that can accumulate and hold 4 charges, 2 positive and 2 negative, using only light at intensities close to real sunlight. It's an achievement that addresses one of the biggest bottlenecks in the field, and it could reshape the future of renewable fuels. Artificial photosynthesis is different from solar panels. While panels make electricity, this technology aims to make storable fuels such as hydrogen, methanol, or even jet fuel. That's crucial because many sectors, aviation, shipping, heavy industry, are extremely difficult to electrify. To produce these fuels, chemistry requires multiple electrons to be delivered simultaneously. Sunlight, however, arrives 1 photon at a time, so any practical system must accumulate charges and hold them long enough to drive reactions. Until now, most molecular systems either required extremely intense laser light or they relied on sacrificial chemicals that were consumed in the process. Neither is viable for real-world sunlight. The Basel team's breakthrough is a carefully designed 5-part molecule. At its center is a familiar photosensitizer, the ruthenium complex, which absorbs light. On one side are 2 electron donors, a triarylamine and a phenothiazine, while on the other side sit 2 electron acceptors, an anthraquinone and a naphthalene diamide. This layout forms what chemists call a redox gradient. The donors are tuned from stronger to weaker and the acceptors from weaker to stronger. The effect is to channel charges step by step away from the photosensitizer once light hits it. Here's how it works in 2 steps. When the molecule absorbs its first photon, the excited photosensitizer passes an electron to the anthraquinone, leaving a positive charge on the phenothiazine. Then, through downhill transfers, the triarylamine takes over the whole and the electron slides further out to the naphthalene diamide. The result is what the team calls charge-separated state 2, 1 positive charge stored on the triarylamine, 1 negative charge on the naphthalene diamide, and about 4.4 nanometers between them. That separation is large enough to suppress recombination, giving this state a lifetime of roughly 120 microseconds. In chemical terms, that's an eternity, plenty of time to absorb another photon under sunlight. When the molecule absorbs a second photon, something remarkable happens. The nearby donor and acceptor, phenothiazine and anthraquinone, are neutral again, so they become the preferred sites for new charges. Kinetics, the speed of electron transfer, now beats thermodynamics. Instead of recombining with the existing charges, the second excitation moves a new electron onto the anthraquinone and leaves a new positive charge on the phenothiazine. Suddenly, the molecule is holding 2 holes, 1 each on triarylamine and phenothiazine, and 2 electrons, 1 each on anthraquinone and naphthalene diamide. This charge-separated state 3 stores nearly 3 electron volts of energy, about 290 kilojoules per mole, and it lives for up to a microsecond. It may not sound long, but it's long enough to engage in chemical reactions, especially once catalysts are attached. What makes this so important is the timing window it opens. In older molecular systems, 2 photons had to arrive within 10 picoseconds to 10 nanoseconds of each other, something only a laser can deliver. Here, the first charge pair survives for over 100 microseconds, a difference of 4 to 7 orders of magnitude. That means sequential excitation is possible even under weak continuous light, close to real solar irradiance. For the first time, a purely molecular compound has demonstrated true stepwise charge accumulation under sunlight-like conditions. The researchers verified this using a clever combination of techniques. Cyclic voltammetry established the redox ladder between donors and acceptors. Spectroelectrochemistry provided the fingerprints of each oxidized and reduced fragment, which were later matched to signals in photoinduced experiments. Transient absorption spectroscopy captured the long-lived separated state after the first photon. Finally, a continuous wave laser was used to populate that state steadily, and a pulsed second laser probed what happened when a second photon was added. The appearance of new spectral signatures corresponding to both phenothiazine and anthraquinone radicals confirmed that the molecule had indeed stored 4 charges at once. Of course, this is not yet a full artificial photosynthesis system. There are no catalysts attached to actually split water or reduce carbon dioxide. The molecule works in organic solvent under controlled conditions, not in a device. And its core photosensitizer, ruthenium bipyridine, is excellent for experiments, but not ideal for large-scale deployment because of cost and abundance. Still, as Professor Oliver Wenger, who led the project, emphasized, this is a crucial piece of the puzzle. For the first time, researchers have shown that sequential light absorption can load a molecule with multiple charges under weak light without sacrificial additives. The implications are profound. In the future, molecules like this could be connected to catalysts that perform multi-electron chemistry, 4-hole water oxidation to release oxygen, 2-electron proton reduction to make hydrogen, or multi-electron carbon dioxide reduction to create synthetic fuels. If scaled up and stabilized, such systems could provide a direct path from sunlight to liquid fuels, fuels that fit into our existing infrastructure but no longer add carbon to the atmosphere. Unlike batteries, which are heavy and expensive to store at scale, solar-derived fuels could be shipped worldwide, used in long-haul transport, and stored seasonally, solving the intermittency problem of renewables. Other countries are already experimenting with artificial photosynthesis. Japan is investing in photocatalyst research as part of its hydrogen strategy. The European Union has funded projects to make aviation fuels from sunlight. Laboratories in the United States have developed prototypes for solar-driven hydrogen production, but scaling has been difficult, both because of efficiency losses and the high cost of materials. The Basel study doesn't solve these challenges overnight, but it shows a pathway toward molecular systems that can operate under real sunlight, something long thought out of reach. In short, what the team has achieved is charge banking, the controlled stepwise storage of multiple redox equivalents in a single molecule, powered only by visible light. It's not yet the artificial leaf, but it's the leaf's beating heart, now proven to work under sunlight-like conditions. Each breakthrough like this brings us closer to a world where fuels no longer come from fossil carbon, but from sunlight captured directly in molecules. The question now is how fast this can move from elegant chemistry to practical technology. Could this design, or ones like it, be the foundation for real artificial photosynthesis reactors? Could they finally give us the storable, carbon-neutral fuels we need for planes, ships, and industry? Whatever the timeline, this discovery is more than a scientific curiosity. It's an advance with the potential to change the way we think about solar power and energy storage forever.